Thank you very much, Jose Carlos. It's a great pleasure to be here and giving this talk. I have to, I'm going to be talking some common things that I talk already in Villahermosa and in Oaxaca, but I've made some changes and hope this is going to be a little bit a nicer talk. But okay, so the idea is that I'm going to be talking about Farber's topological complexity, its properties, and then ways to try to compute it by using computational methods, by using a computer, actually. So the way that I'm going to be doing this is by presenting first the very general properties and highlights of this concept. And then I'm going to be showing 3 examples that I hope will be enough for motivating the presentation of this discretized version of Farber's topological complexity. So let me begin by recalling what this thing is. Topological complexity of X, TC of X, is just the sectional category of the fibration that is given by double evaluation at the endpoints of a given path. Namely, E01 is the fibration going from the path space on X, this is free paths, down to X times X, and it sends a path into its initial and final points. Now, what is the sectional category of a fibration or a map in general? Well, what you have to do is consider open coverings of the base space. In this case, it would be X times X. Consider open coverings of X cross X, and take only those coverings which are formed by open sets which admit a section, a local section on that open set of the fibration under consideration. So, and just for normalization purposes, one takes one less than that number, so that a fibration admitting a global section would have sectional category being 0. So this is the topological complexity of a space. So what's the idea behind this, and what is the relationship with motion planning? Well, in the case of the double evaluation map from Px down to X cross X, well, we have to take open sets, open subsets of the Cartesian product where the double evaluation maps admit a section. Well, the idea here is that Farber's motivation for this concept is that you can think of X times X as being the space of motion tasks of a given autonomous system. And then the total space of the fibration, Px, would be the action space, namely all possible movements of the robot, the given autonomous system. And having a section, or a local section, would be having a rule that assigns to each task of the robot an action that solves the task. So, okay, so this is, and then you are looking for the minimal number, -1, of these local sections. And that's that number, it would be just the topological complexity. Usually for mathematical purposes, and so far from the experts, they only care about this number. But it would also be interesting to know explicit sets of open coverings with corresponding sections that solve this motion planning problem. Now, what's the idea behind this? Is, of course, sections have to be remain in the topological category, so they have to be continuous. And that means just that you have to have local sections, or let me call them local motion planners, which have to be robust to noise, in the sense that small perturbations of the task should result only on small changes of the actual action solving this task. So all in total, topological complexity would be a way of measuring the complexity of motion planning for autonomous systems that perform in unnoisy environments. Okay, so that's basically the main idea. So how am I doing? Is everything, everybody's listening clear?
Yeah, it's fine.
Okay,
Yeah,
okay. All right. So, okay, so let me continue. Now let me observe that a local section S from U to P of X is nothing but an old homotopy. Namely, you can take the two projections from the Cartesian product of x times x into x, the two projections, and restrict them to U. So you have there two maps. And a section, as the one that is shown in the screen, would be nothing but a homotopy. Namely, this section has two parameters, one which is the point of U, and then it has a time parameter. And at the beginning of the parameter, it has to be the first projection, and at the end of the parameter, it has to be the second projection. So that this is a requirement for being a section of the double evaluation map. So all in total, this means that a motion planner, a local motion planner, is nothing but a homotopy between the two restrictions of the projections. So, and in fact, this invariant is indeed a homotopy invariant effect. It has to do a lot with homotopy properties happening on X. So let me very briefly highlight some of the main properties of this concept. First of all, it is a close relative of the LS category of a space X. Namely, if you take the double evaluation map and restrict it through one of these sections, namely you send a point Y into a fixed point star comma Y, then the restricted vibration consists of those, the total space of this restricted vibration consists of those paths that start in the given fixed point. And of course, this is a contractible space, and having local sections for that means identifying open sets on X, which are contractible on X. So this is the relationship between the topological complexity of X and the category of X. Of course, category is an old concept from the 1930s, that has to do with having lower bounds for the critical points of smooth functions on a given manifold. And this somehow is recovered by this double evaluation map, which is motivated by this robotics problem. Well, anyway, having this pullback diagram just means that one already has this inequality. Namely, the topological complexity of X is somewhere in between the category of X and twice the category of X. And I already said that category is recovered from topological complexity, and indeed, topological complexity carries more information than the category. And just to give an example of why this is so, suppose you take two numbers, C, little c, small letter C, and T, which satisfy this inequality. T is somewhere in between C and twice Z. Then it is a known fact that I already heard from Dan Cohen in 2013, that there is always a space X whose category is C and whose topological complexity is T. So in other words, there are a lot of spaces with the same category C and whose topological complexity can take any value that you really wanted in advance in between C and 2C. So in a sense, topological complexity is less rigid, and of course it recovers category. And here's another example that I like, and it will be important for what I'm going to be doing later in the talk, that the category of spheres, which is one of the favorite objects for an algebraic topologist, the category of one of these spaces is 1 because these spaces are made up of two contractible spaces, whereas the topological complexity of a sphere is either 1 or 2, depending on the parity of the dimension of the sphere. And actually, proving this is not that very difficult. It was already done by Michael at the beginning when he introduced these ideas. But understanding the homotopy nature of this fact has to do with understanding the relationship that a certain generalized Hoff invariants have to do with topological complexity. But one of my favorite examples, also a result of Farber and Tabachnikov and Jusbinsky, is that whereas the category of real projective space of dimension M is easy to compute and realize that it is M, topological complexity of this space is a much more interesting number that has actually got the attention of algebraic topologists from the 1960s. Namely, the topological complexity of RPM is nothing but the minimal dimension of Euclidean spaces where these manifolds, RPM, admit an immersion, a smooth immersion, except for three special cases. And not only that, but topological complexity admits many equivariant versions, and one of which is known as the symmetric topological complexity, actually captures the embedding dimension of real projective spaces. So this is a very nice concept, motivated somehow in a very nice, simple way by robotics, but having to do with actual classical mathematics. So now let me start discussing some of the applications that I have in mind to introduce this discretized version of the TC. So let me talk about a little bit just about Cartesian products. The category of a product is bounded from above by the sum of the categories of the factors, and well, you can have strict inequalities. That's not much of a problem, but this is a problem of having spaces of different torsions in the homology. So one of the questions that one could ask is, well, say that one of the factors has no torsion in its homology, say it's a sphere. And then the category of X times a sphere would be bounded from above by the category of X plus 1, because the category of the sphere is 1. And for a while, it was a conjecture whether or not, well, whether this would be an equality for all spaces X. And it was known to be an equality for many spaces, namely many classes of manifolds and other formal rational spaces also had this property. But in 1998, Noriwase realized that actually there are examples, homotopically simple examples somehow, where inequality actually holds. And I'm going to be saying a little bit more about that, but then you could ask the same question for TC. Topological complexity of X times Y is also bounded from above by the sum of the topological complexity of the factors, and then you could take one of these factors to be a sphere, and then the topological complexity after crossing with a sphere would increase at most by 1 or 2, of course, depending on the dimension of the sphere. And one of the results that we got with Lucille and Mark is that Mark Grant is that topological. There is also examples. What you would expect expecting that this inequality is always an equality is false. You can cook up examples where this is false. And to say a little bit about those examples, let me say what's the main idea, just a very rough main idea of what is behind Iwase's work. Namely, the counterexample of Iwase is take this two-cell complex, take a sphere of dimension P and attach a cell of dimension Q plus 1 by a map alpha. Now, one of the things that when computing category of a space X, one of the things that Whitehead and Bernstein realize is that you have canonical obstructions to deciding whether or not how the category behaves when you attach a cell. And indeed, this is a very nice way of understanding category of a space. Start understanding category of the skeleton and then see how it increases after attaching a bunch of cells. After all, if you attach a bunch of cells, you're attaching a cone, so the category can increase at most by 1. So what happens is that if you think of X cross a sphere, then in this figure of dots, this picture of dots, I have here on the slanted line going to the left, I'm thinking here of the cell structure of X, namely it has a cell in dimension 0, one in dimension P, and one in dimension Q plus 1. And then I cross it with the cellular structure of the sphere, so I have this picture. And then one has layers, namely the first layer is formed by the cell, which is the product of the two base points, which I'm denoting here as 0, 0, and so on. So by the time when you attach the purple dot on the axis of X, you are asking whether or not the category is either 1 or 2, whether it can increase by 1, because in the previous layer it was 1. And then what Norio did was to choose a attaching map whose invariant, namely whose Hopf invariant, this obstruction, is non-zero. Okay, this is good so far, but then you can think of the whole Cartesian product. And then you have a top dimensional cell in red here, which you have to decide whether or not the category goes from 2, which is the second layer, to 3. And it turns out that the obstruction for being remaining being 2 is 0, because it is actually, and this is the main work of Iwase, is that this obstruction is just a suspension of the previous obstruction. So the obstruction is 0, and then you get that the category of the Cartesian product stays being 2, just as the category of X. So this is just a story made short of long, very technical computations, but using the same kind of calculations, you can generalize Hopf invariance and prove that you have also counterexamples to what would be the TC Ganea conjecture. Namely, the space is a stunted projective space with 4 cells, not 2 cells, like in Norio's example. Take a real projective space in dimensions from 3 to 6, and then if you take the wedge sum of this space with itself, then it turns out the topological complexity of X is 4, but if you cross it with an even dimensional sphere, it only goes up by 1, whether recall that the topological complexity of a sphere would be 2, of an even sphere would be 2. So this goes lower than expected. And this kind of ideas allows one to actually describe the topological complexity of two-cell complexes in the metal stable range. All right, but this is actually a little bit technical, and the idea here is that this involves a lot of homotopy computations. Our computations sometimes.
Jesus.
Yes. Yes.
One question. I think I always ask you this question, but I always forget the answer. What do we know about the Ganea conjecture for closed N manifolds? I mean, for manifolds.
I don't think that it is known to be true for all manifolds. I think you need some additional hypothesis, but I'm not sure. I would have to double check. I'm not sure.
Meaning, is it? Are there counterexamples of Ganea conjecture for manifolds?
Not that I know.
Okay.
No, not that I know.
Okay. Okay. Fine. Thank you.
Mm-hmm. And it's possible that it's not known a counterexample for manifold, for being an actual manifold.
Okay. All right. Fine. Thank you.
Okay. So I want to replace this, the use of these homotopy theoretic tools for understanding just the value of this invariant TC of X by more computational techniques. But still, I'm going to say one further thing about the general technique for computing these numbers. Namely, topological complexity of X can be estimated both from below and from above by a couple of invariants. The first one on the left is called the zero cup length of X, and is a close friend relative of the cup length, the usual cup length, which is related to category of a space. But let me just say that this comes from cohomological information from X. And being cohomological, singular cohomological, you can take generalized cohomology or any cohomology that you may want with products. But anyway, this is usually accessible. On the other hand, if you want to estimate this number from above, then you have to actually use some homotopy information. And there is a general upper bound given by the twice the dimension of x, or the homotopy dimension of x, divided by the connectivity of x plus 1. That gives you this estimate for the topological complexity. And well, this of course already involves homotopy information. But in many cases, computing the topological complexity of x actually amounts to improving either one of these bounds. And when you actually need to improve the upper bound, then you get into real hard land, because then you have to use some kind of some version of obstruction theory and start dealing with the complications inherent to this theory. So in general, this is not very pleasant unless you are really very lucky way to approach this problem, but it's a very, very strong way, but hard to deal with. So the alternative that I want to propose is, well, of course, I don't only care about computing this number, but I would be interested in describing actual motion planners, namely systems of local open sets with the local sections describing how to move in a robust way to the noise. And not only that, but I want to do this with the help of a computer. So I don't have to think about how to do it, just program the computer to search for these things. So what I'm going to be doing now is to talk about these three examples. I'm going to be talking a little bit about collision-free motion planning, and then a flat version of it, which can be thought of motion planning with control interactions of the robots. And then I'm going to be saying a little bit about robot arms with combinatorial restrictions, and I'm hoping to convince you that these three examples motivate the need of saying, well, okay, let's have a way of putting a solid ground where to start programming computers to look for these things. So let me start with the first thing. Let me go back again with products and recall that the topological complexity of a product is bounded from above at the sum of the topological complexity of the factors. This fact is more or less easy to see. It amounts to, well, if you look at the vibration on the left of this commutative diagram, then you have the double evaluation map for the Cartesian product. Namely, I want to understand the sectional category of this, which is the topological complexity of x times y. And of course, the base space of this vibration is nothing but x cross x times y cross y. So I'm just switching the two middle factors. But also a path on x cross y is only a pair of paths, one in x and one in y, namely the components of this path on the Cartesian product. And this inequality just says that the sectional category of a product of vibration is bounded from above by the sum of the corresponding things. Proving this is more or less easy, but let me just not say anything about that. Just say that if you want to motion plan two robots simultaneously, then it is more robust, it is robuster to do it simultaneously, because then you potentially need less local rules. So simultaneous motion planning is robust for purposes of noise. But now suppose that I have these two robots, namely R and S, that I should have said, one having configuration space X and one having configuration space Y. But now assume that X and Y are the same. And not only that I have two robots, but I have N robots. And that they are moving in the same space and they have to be distributed in somehow, but I want to avoid collisions. So what is the natural space of states of this system of robots? Well, this would be the classical configuration space of X on N elements, N points, which avoid collisions. Namely, two different coordinates can never be the same. And a nice example of this situation would be the problem in a factory floor where you have, say, three robots, one red, one yellow, and one green. They are moving on the top square on this picture. They are moving. This is the floor of the factory, and they have to be distributed to the different teams that are working in this factory. Now, suppose that the time goes from top to bottom, from 0 to 1, and as the robots move, and if I put this third dimension, then their path describe this braid. So what I'm saying is that the configuration space of endpoints on R2 precisely has fundamental group given by the classical arting group of pure braids. And this is a very interesting space for the eyes of a topologist, because not only its fundamental group is the classical arting group of pure braids, but it doesn't have any higher homotopy groups. Namely, you have here a KPN, 1 space. And of course, I said that the topological complexity is an invariant of the homotopy of the spacing under consideration. So you understand the topological complexity of this K pi 1 space amounts to understanding the algebraic properties of this group, of this Artings group. And well, it is known what the answer is, and here is the answer. In the case of the classical Arting group, the category is well known that the category of Pn is, meaning the category is of any classifying space of this group, is n minus 1, and the topological complexity is not twice that, but only 1 less than that. And this is a work of Farber and Jusbinsky. And then, if you want to generalize, recall that Pn is the fundamental group of this type of the configuration spaces of endpoints on the plane on R2. And if you want to take under consideration general Euclidean spaces, then the configuration space of endpoints in Rd has category also n minus 1. This is also more or less well known, easy to see. And the topological complexity of this space, even when the dimension of the Euclidean space goes higher, stays being the same, basically the same. Namely, it only depends on the parity of the dimension of the Euclidean space. It is either 2n minus 2 when the dimension of the Euclidean space is odd, or it is 2n minus 3, otherwise. And of course, proving the case when D is odd is easy, because this is the upper bound that you would have by the dimensional or the category. Recall that the topological complexity is bounded from below by twice the category. So you already have the category is n minus 1, and you have 2n minus 2 as the upper bound. And then you have to do a little work to show that by cohomological computations, this is also a lower bound. But the hard part is when the dimension of the Euclidean space is even, or for that purpose, when it is 2, and you're back in the case of Artin's group. So here is just a very rough idea of the proof of what you do. Namely, it amounts to considering only the case of the plane, not only R of an even dimension. Namely, because you can use a little bit of obstruction theory to realize that the obstruction is independent of D as long as it is even. So you can just concentrate on the case where the dimension is 2, is actually 2, and then you can do a little bit of happy plane arrangements. And I might not have enough time to say things about that, but essentially you realize that the space of configurations of the plane, think of it as configurations of the complex plane. Well, this is, of course, the complement of a complex arrangement. And then you can projectivize it. Namely, you have the action of C star and take the quotient. And then you have here the quotient would be just the projectivized arrangement, which, of course, this lives in the projectivization of Cn by the action of S1. And you're removing some of the lines in the arrangement, and just by removing one line, you get that you have one of these affine charts. And at the end, you realize that the projectivized arrangement is nothing but a standard arrangement in Cn minus 1. So that rank goes down by 1, and the rank is well known, and a deep theorem to be giving an upper bound for the dimension, the homotopy dimension of that. And this does the trick because this fibration, this principal fibration, admits a section, and so it is trivial. And then you realize that the total space, namely the configuration space that you wanted, is just the Cartesian product of S1 and the projectivized arrangement. That does the trick. Okay, but anyway, the point that I want to understand here is that you use some information, this geometric information from the complex case to say something about this theorem, and then use obstruction theory. The first way of approaching this is obstruction theory to extend it to other even dimensions. But again, I want to avoid this. And there is a known way to avoid the use of homotopy theory. Namely, after this result was known, a pair of students, former students, master students from CINVESTAV, got, using some ideas of Michael Farber about configurations of graphs and trees, these guys, Mas and Giese, constructed explicit motion planners for the case when D is odd. And then later on, about a couple of years ago, Michael extended this to construct explicit motion planners for any D. So this can be done, although, again, by human intelligence. Namely, these are ad hoc motion planners for this case. Now, let me mention this second example. This is the case where I have controlled interactions, controlled number of collisions. Notice that I am not, in what I just said, I'm not considering the case of configurations of R, of endpoints in R, because this is not a connected space. And if I want to plan the motion, I better have paths joining any possible pair of points. But now what I can do is restrict the definition of configuration spaces so to allow a path-connected space. And I'm going to be doing this by the following. It's a standard way of extending the notion of configuration spaces. Namely, consider the Cartesian product x times xl n times, and fix a subset sigma of points on one from from 1 to n. These are going to be these are to be thought of the factors of the Cartesian product. And then consider this kind of diagonal, partial diagonal, defined by sigma, this sigma, which is just the diagonal consisting of those n tuples for which these d+1 points in the coordinates I0 up to ID are all equal. This is a partial diagonal. All right, with this definition, then what I can do is suppose now that I not only have these vertices 1 to n, but I have a simplicial complex K. Then I want to define what would be the K, the configuration space of endpoints on X with controlled interactions controlled by K. And this would be just the intersections of all these partial diagonals running sigma over the non-faces of K, the complements of those things. So this is just imposing restrictions on which ones, this is the complement. So I don't want these kind of equalities depending on the non-faces of the simplicial complex. So what are the properties of these generalized configuration spaces? Well, they are monotonous. Namely, if L is a subcomplex of K, of course, L has less faces, but K has, but then L has more non-faces. So what I'm doing here in describing the configuration space of type L, I'm imposing more conditions, namely more intersections, more conditions on the intersections. So this amounts to saying that these generalized configuration spaces modeled by these simplicial complexes are monotonous in this sense. And not only that, but for instance, if my complex is the whole simplex on n vertices, then it doesn't have any non-faces, so I'm not imposing any restriction, so I recover the full Cartesian product. On the other hand, if the complex is just the zero skeleton, then any simplex with at least two vertices is a non-phase, and I avoiding this kind of collisions, so I recover the classical configuration space. And in particular, I would be interested in the configuration spaces that are obtained by considering the k-2 skeleton of the complete simplex. And these, of course, are configuration spaces where no k-multiple collisions are allowed. And in particular, just being a little bit more in particular, let me consider the case of configurations of R with n points controlled by the skeleton, the one-dimensional skeleton of the full simplex, namely the complete graph. So what I'm doing here is I'm avoiding collisions of 3 points because this is the graph. So 2 points, 2 vertices are allowed, they are faces, but 3 vertices are non-faces, and I don't want those kinds of collisions. So this is the configuration space of no 3 equal points on R, on the real line. Now, these kind of spaces are also old. They have been considered in work by Björkner and Lovas. They studied the complexity of algorithms for the problem of deciding whether n real numbers are equal, whether n numbers have k equals repetitions. But from the point of topology, these configurations 3 Rn are really very interesting because these are the flat analog of Artin's braid groups. Namely, these spaces are aspherical. Their fundamental group is the only non-trivial homotopy group these groups have. And here are a couple of pictures. Namely, I have, so suppose n is 3, I have 3 points, one which is red, one which is yellow, and one which is green. And then these 3 points can be moving along this line, which starts on top and then go down to the bottom as time progresses. And at each time, there can be at most 1 collision, not 3 collisions. So for instance, at the very beginning of the picture on the top right left, the yellow point and the green point are crossing each other, and so on. And then you can smooth this, and what you see is that you get a planar version of a braid. And these are indeed precisely known as planar or flat planar braids on 3 strands. And then you have this group, you have the corresponding theory for these groups, and then you could ask, well, what is the topological complexity, or say the category of these groups, namely what is the topological complexity of the classifying spaces of these groups. And this is a new result that we got with a couple of colleagues, Barbara Gutierrez and Christopher Roque, which are recent PhDs from our department. Namely, topological complexity of these groups, these flat braids, pure braids, are always twice the integral part of n over 3, except in a special case where n is 3. In that case, you actually have if n is 3, then this answer would be 0, and the space is not contractible. It's actually a circle. So this is the only special case. So let me just say why I'm mentioning this example and start discussing a little bit of the discretization. I'm mentioning this example because improving this kind of result, you, of course, use the estimates, the lower estimates and the upper estimates that I mentioned briefly, namely the lower estimate given by cohomological information. If the cohomology of these groups, of PPN, is known, it's the cohomology even as a ring is known, and this is what one needs. And the answer that you get for the lower bound is precisely twice n minus 3. But then you would have to know that this is also the upper bound. And this actually is a little bit trickier because, well, work of Sievers and White, they constructed a cellular complex, which is a homotopy model for the configuration, for the classification, for the classifying space of this group. Unfortunately, this model has higher dimension of n over 3 integral part. But then you can do those two things. Either use this model to feed in a computer to actually come out with this answer of of a motion planner with these many local rules, or still rely on the work of Sievers and White. They use this cellular model for the classifying space of this group, and then they use a discrete Morse theory to produce actually a minimal model, which actually has dimension n over 3. And that gives you actually from on the nose that this is also the upper estimate and gives you the right answer. So in a sense, this way of proceeding is similar to corresponding discretizations that Nessa is pursuing with her group, on using discrete Morse theory directly on the nose of producing motion planners for the same purposes that I'm after in this talk. All right, so this is the second example, and the third one has to do with actual robot arms with combinatorial restrictions. Now, my time is getting short, so I'm going to try to summarize what is the point here. The point here is that you can actually compute the topological complexity of more complicated robot arms, which have certain restrictions. For instance, the kind of restriction that these robot arms are that not all the elbows can move at the same time. If some elbows are moving, then some other elbows have to stay close to the neutral position. And the spaces that arise from this kind of robots come from toric topology. They are known as polyhedral products. And computing their topological complexity is known by work of Dan Cohen and a student of his, last name Fruzzi. And they describe the topological complexity of these polyhedral products. And the answer is rather explicit, and it actually agrees with the lower bound given by cohomological information. So this is an example where you have to improve the upper bound given by homotopy information. However, because of the nature of this answer, the answer can be as far away as you can imagine from the very natural upper bound given by the homotopical dimension. So if you want to do this, prove this theorem just by obstruction theory, you would be in very hard land. So what Cohen and Pruzzi did was to actually produce explicit algorithms for producing local rules for planning the motion. So, and not only that, but these kind of results are generalizable to higher topological complexity, and also scream out for the need of having a way to produce algorithms, ways of producing motion planners in a more systematic way. So this is actually then finally the motivation, and let me just start now by saying what are the main ingredients for discretizing the notion of topological complexity. I call this the simplicial complexity because it applies for simplicial complexes, abstract simplicial complexes, instead of topological spaces. All right, so this model is based on barycentric subdivision. Barycentric subdivision plays a central role in discretizing Farber's topological complexity, and it captures this concept. And it can be implementable, being already discrete, is computer implementable, and can be used both for proving results in the theory, for instance, in the examples that I mentioned briefly, or for actual applications in real life. But one of the drawbacks of this thing is that it has a huge search space, basically because you are taking into account barycentric subdivision, and this makes terrible. But on the other hand, this not being a drawback, I see this as an interesting point because then it calls for the use of other techniques in optimization, for instance, looking forward for heuristics for searching in this huge space, This could be used, for instance, discrete Morse theory techniques or any other kind of technique. So let me just say what are the basis of what the basis is for these ideas. And well, suppose K, now K is not a space, it's an abstract simplicial complex. And I'm going to be thinking of its topological realization. And of course, I want to consider this diagram, which is the basis for understanding topological complexity. Well, but I want to discretize everything. So the first thing to discretize is the base space of this vibration. And I can do this by taking the Cartesian product simplicial structure on K, as long as I take in the category of abstract simplicial complex with an order, so that the realization of the product of that simplicial structure is just a product of the corresponding realizations. So this is okay. Then I have to understand, I have to take open sets and local sections on them. Now, since this is a nice space, it's a polyhedron, open sets are safe to be replaced by realizations of subcomplexes. So let me just take subcomplexes J. And I want to take local sections, like in this picture. If I want to understand, honestly, a local section, I would have to first to understand a way to discretize the codomain of this map, namely the space of paths on X. And this would be just impossible because this space is too large for having a finite dimensional, finite simplicial structure. But instead of doing that, let me just use the fact that I already mentioned at the beginning of the talk, namely a local section, a map S is nothing but a homotopy between the realizations of the restrictions of the two projections. Now, of course, a homotopy doesn't have to be simplicial, but after all, a homotopy is a map. And one thing that I learned from NESA some years ago was that, well, maps, just as spaces, can be approached simplicially. So let me just review what the main theorem is behind all this. Namely, suppose you have two simplicial complexes, J and K, and you have a map between them. All right, then any such map, this is a continuous map, of course, between the topological realizations. This is a map between topological realizations. Then any map can be approximated by a simplicial map, simplicial in the category of abstract simplicial complexes, as long as you allow yourself to subdivide fine enough the domain. And let me just explain this picture in this, here, in this idea in this picture. So let me go up. And the idea is, okay, so suppose J is the triangle in red on the left, and that K is this triangle annulus on the right. It doesn't have the central triangle. This is empty, but everything on the annulus is filled in. Now the map under consideration from the realization of J to realization of K is the map which is suggested by this red triangle. It sends this red triangle on the left to the red triangle in the obvious way on the right. Now this is not a simplicial map because it doesn't even send vertices into vertices, but it can be approximated in the following sense. Namely, notice that this edge of the triangle has a property that you can divide it into three pieces, and each one of the three pieces goes into corresponding three triangles on the left side of this annular triangle annulus. And then you can consider the simplicial map suggested by the darker red line, and this approximates the original map in the sense that each of the three segments in which you divided one of the sides of the left triangle is sent into one common triangle. And then you can move one to each other just by a linear movement because you are inside a triangle. So this is in this sense, you're approximating simplicially this part of the simplicial map, and then you can generalize this. And here I'm exhibiting a approximation, a simplicial approximation for the original map. Now, it's easy to describe, although not so easy if not in a blackboard, to describe different approximations. But the point is that any two approximations of this sort are contiguous in the sense that they also have the same property. Namely, they send simplices in the domain into simplices in the codomain, which lie in a larger simplex. And then these two simplices can easily be moved from one to the other. All right, so two approximations of a given simplicial map are contiguous, one contiguous, and of course, being one contiguous, they are homotopic by linear movements. And you can extend this to equivalence relation and consider these equivalent relations of contiguity classes. And then, more importantly, is this third point in this theorem, namely that two maps are homotopic if and only if, well, if you allow yourself to subdivide fine enough the domain, then they admit approximations which are in the same contiguity class. So all in total, what this does for you is to reduce the problem of saying whether two maps are homotopic to saying whether or not these maps lie in the same contiguity class. So, well, I've discretized the problem of describing local motion planners. Of course, the idea here is to think of this graph where the vertices are the simplicial maps and where edges are put as long as these simplicial maps are contiguous. And then what I'm saying is whether two of vertices lie in the same path component of this graph. But the problem here is the graph is huge because you're allowing yourself, you might need to allow yourself to subdivide large enough. But anyway, everything is on the table, and I can do the main definitions in 5 minutes. And well, fix a couple of numbers, B and C. B is going to stand for the number of subdivisions that you're going to allow yourself, because I'm interested in programming this, implementing this into a computer. So, well, I'm going to give a limit on how many times I need to subdivide. And this is better a small one because this quickly goes out of control. C is going to stand for the length of contiguity chains that I'm willing to look for. And then I can define the simplicial complexity of type BZ of K as the smaller number of subcomplexes J of K times of the subdimension of the minimal number, the smallest number of subcomplexes J covering the B times subdivision of K times K in such a way that the two projections from the subdivision into K restricted to J are chain contiguous by a chain of length at most K. So this is this number, the simplicial complexity, so control. And then one can show more or less easily, this is standard techniques in combinatorial topology, that as long as you increase by 1 the number C or the number B, this number go down. So you have this monotonous sequence of things, of numbers, and you can take the limit of them as B and C goes to infinity. And define the simplicial complexity of K as the corresponding limit. And then the main theorem is that the simplicial complexity, so defined, agrees with the topological complexity of the geometric realization of the complex. So let me finish just by a couple of comments on what are the complexities of this thing. Of course, this is a bad thing. Take a limit or as B goes to infinity, because then you're needing to subdivide as many times as you need, and well, this quickly goes out of control for any computer. But the point is that if you try this with, say, a very simple space like the circle, maybe a triangle, if you do not subdivide, then the corresponding simplicial complexity is not the real answer. You need to subdivide once and only once, and this is still doable within hand to realize that you have this equality given by the theorem, and indeed this was one of the motivations for this theorem. And on the other hand, these kind of ideas, so the idea here is that for nice enough spaces that are not so tangled in small neighborhoods, the idea is that you should do good by subdividing a small, really small number of times, 1, 2, perhaps even 3, but not many. On the other hand, there are other versions of these ideas of trying to discretize TC. I already mentioned this work in progress by the group of NESA, but there are also some other approaches, one of which was done by a group of people in Spain, Fernandez, Macia, Minus, and Vilches, which they use Minian's concept of strong collapses, which is also closely related to homotopy problems in complexes, to discretize this problem. But the problem is that they have approximations for the actual TC, simplicially, but they are not good enough because they are not taking into account the subdivision process. And it is apparently a bit hard to do this in terms of Minian's concept of strong collapses. And finally, there is also this work of Tanaka, which developed these discretization ideas for TC within the context of finite spaces. And actually, in the original preprint that Tanaka produced, he didn't introduce either the subdivision process, and I still didn't get that their model, the discrete model, was fine enough to agree with the topological complexity of Michael. But then later on, he produced a version where he introduced this idea of subdividing, and he got the corresponding results. So the conclusion is that essentially one has several ways of discretizing, laying the grounds for actually producing ways of searching for explicit motion planners, namely local rules and local sections for this double evaluation map, to try to apply them for concrete motion planning problems, either in theory or in practice. Okay, well, thank you very much.
Thank you, Jesus. Are there any questions?
I have a small question. Can you hear me? So
yes,
my question is this. Do you have any idea at all in practice how many steps of these barycentric subdivisions would be necessary to come up with the, a good enough approximation of topological complexity? Is it like 1 or 2 or 15 for reasonable simplicial complexes, K?
Yeah, sure. This is a very important question for applications. As I said, in the case of the circle, only one subdivision is good enough. And I have no idea. We haven't yet produced, we have a student, a master student that is producing some implementation of these things. He has some codes, and I still have to try them in some concrete, simple, simplicial complexes. The short answer is that I have no idea. Scientifically motivated. How many subdivisions? On the other hand, I wouldn't be willing to go for 15 subdivisions, not even perhaps 5. Would be just a terrible thing to do. And after all, yes. I'm not interested. This kind of ideas are not interesting for the purpose of computing, after all, the topological complexity, but giving reasonable, as you said, reasonable approximations and explicit motion planners. So perhaps going 1, 2, or 3 subdivisions.
Yes, that's what I thought, that probably 1 or 2 would suffice in most cases. The other problem is that to actually test these things, you're sort of limited to relatively simple simplicial complexes, because otherwise the complexity of the computations becomes very big immediately, right?
That's right. If you want to do a, well, this is the thing that I mentioned. If you want to do full search, would be just out of the question. But then you can do probabilistic random search or any other heuristic. Apply any other kind of heuristics and just do samplings, and then you have a whole area of methods to try on these things.
Thanks.
Any other question?
Hi, Jesus. So
Hello.
in the moment, are you trying then to, the way that your algorithm works, well, there is no actual computer program working right now, but theoretically, in order to compute this simplicial complexity, you have to search through all the possible subcomplexes J that satisfy these conditions. You have to construct them all to get a number. In order to get the number.
Yeah, that in principle you have to do that, and this is also a main problem. The implementation that this guy is doing is only limited. And precisely, it doesn't take into account the problem that you are raising, namely choosing the J's is one of the main problems. Once you have a J, then you would just consider the restrictions and use this algorithm. So this algorithm is not an algorithm for searching the J's, just searching the chain of maps which are gives you this contiguity class. This is so far this program is apparently developed. Now, going back to the problem that you're raising, namely how to choose for J's. Well, these J's have to be subcomplexes, and a complex is determined by the maximal phases. And then there's a finite number of maximal phases, which is usually smaller than the number of simplexes that you actually have to deal with. And of course, each one of the maximal simplexes has to lie in one of the J's. So in a sense, it's more or less natural to think that you would have to be choosing your J's in terms of how to partition the maximal phases of K times K. But no, there is no explicit pseudo code yet programmed for doing this kind of problem.
Would you think that you require like an exponential number of operations to get those states, or just linear?
No, I would think that this would also be exponential, and this would quite quickly go out of control. So again, you have to do some kind of heuristics on this.
Okay, thank you.